The silence that descended upon the astrophysics community in the summer of 2017 was not the silence of awe, but the profound, unsettling quiet that follows the shattering of fundamental assumptions. It was the sound of consensus breaking, the collective intake of breath when a long-held bedrock of theory proves suddenly, undeniably, brittle. The event itself was a cosmic fanfare, the merger of two neutron stars, a spectacular kilonova billions of light-years away, that unleashed gravitational waves, ripples in the very fabric of space-time, detectable here on Earth by instruments like LIGO and Virgo. Scientists were primed for celebration, for the confirmation of general relativity in this extreme environment. Instead, for 3 agonizing days, the data screamed a contradiction, profound discrepancy between the observed speed of these gravitational waves and the theoretical speed predicted by string theory, the reigning champion in the quest for a theory of everything. String theory, in its many iterations, posits the existence of extra spatial dimensions, typically 10 in total, 3 familiar dimensions of space, 1 dimension of time, and 6 curled-up, compactified spatial dimensions. These extra dimensions, often visualized as infinitesimally small Calabi-Yau manifolds, are the scaffolding upon which the universe is built, the mechanism by which gravity, electromagnetism, and the nuclear forces might eventually be unified. The travel time of the gravitational wave signal, precisely measured against the electromagnetic counterpart, the light from the ensuing explosion, suggested a speed for the gravitational distortions that simply did not accommodate the mathematical structures necessary for string theory's favored dimensional geometries. This implied, starkly, that those hidden extra dimensions might be either entirely absent, relegated to the realm of mathematical fancy, or, far more disturbingly, that they are structured in a way so vastly different from the compactified models, perhaps not curled up at all, but extending to cosmic scales, influencing the entirety of the cosmos in ways currently beyond our perceptual grasp. This event, GW170817, did not disprove string theory outright, for the theory possesses an almost uncanny mathematical flexibility, but it did place severe constraints on the simplest, most popular models, forcing a reckoning with the implications of non-locality and alternative dimensional architectures. To understand the weight of this momentary silence, one must appreciate the desperate need for extra dimensions in modern physics. The journey began long before the cosmic collision, harkening back to the early 20th century, a period of intellectual ferment where the Newtonian worldview was being systematically dismantled by relativity and quantum mechanics. In 1919, a German physicist named Theodor Kaluza, working in relative obscurity, undertook an act of breathtaking intellectual audacity. He took Albert Einstein's masterful, four-dimensional equations of general relativity, the description of gravity as the curvature of space-time, and inexplicably, without empirical justification, he augmented them by introducing a fifth dimension. Most physicists dismissed this as mathematical whimsy, a needless complication in a reality clearly perceived in 3 spatial dimensions plus the relentless march of time. Yet, when Kaluza solved the resulting 5-dimensional field equations, the outcome was so elegantly compelling that it could not be ignored. The 5-dimensional equations naturally decomposed, spontaneously splitting into 2 distinct, recognizable sets of equations within the remaining 4 dimensions. One component perfectly described Einstein's gravity. The other component, with startling precision, described electromagnetism, the force governing light, electricity, and magnetism. Gravity and electromagnetism, 2 seemingly disparate fundamental interactions, were revealed to be mere facets of a single, unified geometric structure existing in 5 dimensions. Kaluza proposed the radical solution for why we do not perceive this 5th dimension. It must be compactified, curled up into a minuscule, unobservable loop, its circumference smaller than any conceivable measuring scale. Imagine a garden hose viewed from a mile away. It appears as a one-dimensional line. Only upon closer inspection, only when possessing the spatial resolution of an insect traversing its surface, does the second, curled dimension reveal itself. If this loop were smaller than the Planck length, which is roughly 10 to the power of minus 35 meters, it would remain forever hidden from our instruments. This initial vision, the Kaluza-Klein theory, was elegant but ultimately stalled, largely eclipsed by the explosive, and immediately productive, development of quantum mechanics throughout the 1920s. The invisible dimension was shelved, deemed an unnecessary complication in the face of the burgeoning quantum revolution. The idea languished until 1984, a period when physics was once again hungry for a theory of everything, desperately seeking to reconcile gravity with the successful, yet fundamentally incompatible, framework of quantum field theory. String theory, which posits that fundamental particles are not point-like but rather one-dimensional vibrating filaments or strings, offered a promising candidate. However, early formulations of string theory were plagued by catastrophic mathematical inconsistencies, anomalies where the theory predicted impossible probabilities, outcomes adding up to more than 100% certainty. Then, during a rather dramatic weather event in Colorado, physicists Michael Green and John Schwartz achieved a breakthrough. They discovered a specific set of internal symmetries, an anomaly cancellation mechanism, that rendered the 10-dimensional theory mathematically consistent, requiring the probabilities to sum precisely to 1. This Green-Schwartz anomaly cancellation was the Rosetta Stone. It elevated string theory from mathematical curiosity to the most intensely scrutinized framework in theoretical physics. String theory, in its most viable forms, demands 10 dimensions, 3 large spatial dimensions, 1 time dimension, and 6 additional spatial dimensions curled up. These 6 hidden dimensions must take on specific, complex geometric configurations known as Calabi-Yau manifolds. These manifolds are the shapes of the extra dimensions, and crucially, the vibrational modes of the fundamental strings, which manifest to us as different particles like electrons, quarks, and photons, depend entirely on the precise geometry of the manifold they are vibrating within. Herein lies the terrifying problem that keeps theorists in existential dread, the landscape problem. Mathematical analysis reveals not a few, but an astronomical number of possible Calabi-Yau shapes. Estimates often hover around 10 to the power of 500 possible vacuum states, each corresponding to a universe with potentially unique physical laws, particle masses, and fundamental constants. String theory, for all its mathematical elegance, fails spectacularly in explaining why our universe is governed by the specific set of constants we observe. Why these 6 dimensions are curled in this particular way, yielding the standard model particles and the observed strength of forces, remains an unanswerable question within the theory itself. It offers a multiverse of possibilities but no mechanism to select our reality. The question remains, do these hidden dimensions truly exist, and if so, what is their physical relevance beyond mathematical consistency? The answer may be imprinted on the very earliest history of our cosmos, during the inflationary epoch. Cosmologists theorize that immediately following the Big Bang, around 10 to the power of minus 36 seconds, the universe underwent a period of hyperaccelerated expansion known as inflation. In an incomprehensibly short interval, some models place it at less than 10 to the power of minus 32 seconds. The scale factor of the universe increased by a factor exceeding 78 zeros, transforming a region smaller than a proton into a volume larger than the observable universe today. If extra dimensions were a feature of reality from the outset, this violent expansion would have dictated their fate. The energy initially confined within these higher spatial dimensions would have been transferred into our 4-dimensional spacetime as the inflation subsided, manifesting as a cascade of new, exotic particles known as moduli. Moduli particles are physicists' spectral boogeymen, hypothetical entities so weakly interactive that their existence is almost impossible to confirm. They interact with standard matter trillions of times less frequently than neutrinos, those ghostly particles that pass through the Earth unimpeded as if it were empty space. A moduli particle could traverse the entire Milky Way galaxy without interacting with a single atom. Because of their profound lack of interaction, once created during the inflationary transition, they would persist almost indefinitely, their relic density reflecting the geometry of the primordial, 10-dimensional cosmos. For a fleeting but crucial microsecond, the universe was not merely 4-dimensional, it was genuinely 10-dimensional, dominated by the energy density stored in these extra spatial degrees of freedom. As these moduli slowly decayed, they produced the particles and energy density we observe today, including the theoretically predicted but still elusive axion. Axions are ultralight, weakly interacting particles theorized to solve a different problem in particle physics, the strong CP problem, but they also serve as a potential fossil record of that higher dimensional infancy. Current experimental efforts, such as the axion dark matter experiment, employ massive, superconducting magnetic fields, hoping that one of these ancient axions, drifting through the laboratory space, might occasionally convert into a detectable photon upon encountering the intense magnetic flux, offering indirect, yet undeniable, proof of the extra dimensions that shaped our first moments. But the evidence, or rather the conceptual necessity, for higher dimensions extends beyond the spectral echoes of the Big Bang and the theoretical elegance of unification. It strikes at the very heart of quantum reality, entanglement. Quantum entanglement, famously dubbed spooky action at a distance by Einstein, demonstrates that two particles, once interacting, remain linked regardless of the spatial separation imposed upon them. Measure a property, say, the spin, of particle A here on Earth, and instantaneously, the corresponding property of particle B, now located near the Andromeda Galaxy, assumes the correlated state. This instantaneous correlation appears to violate the cosmic speed limit established by special relativity. Nothing can travel faster than the speed of light. The physical mechanism for this information transfer remains utterly elusive within a purely four-dimensional framework. The radical interpretation gaining traction among certain theoretical camps is that the particles were never truly separated. In the context of higher dimensions, their separation in our perceived three spatial dimensions is an artifact of projection. Picture 2 points on a vast, two-dimensional sheet of paper, miles apart in the sheet's plane. If that paper is folded, bringing the 2 points into immediate contact in a third dimension perpendicular to the sheet, their apparent distance in 2 dimensions becomes irrelevant to their underlying connection. If these entangled particles are simultaneously present in a higher dimensional hyperspace, they remain neighbors, and the instantaneous correlation is merely a function of their proximity in that hidden dimension, not a superluminal communication across the void of our perceived space. This conceptual leap forces us to reconsider the size of these extra dimensions. The constraints imposed by the neutron star merger seem to rule out extra dimensions that were only modestly larger than the Planck scale, as such dimensions would have caused the gravitational wave speed to deviate noticeably from the speed of light in a way that GW 170817 did not permit. However, this only restricts the intermediate scales. Two extremes remain robustly possible: either the dimensions are still microscopically small, curled up beyond our ability to probe, or they are unimaginably vast. If these extra dimensions extend to macroscopic or even cosmic scales, the implications for gravity are revolutionary. The fact that gravity is demonstrably the weakest of the four fundamental forces, a million billion times weaker than electromagnetism, for instance, has long been a profound puzzle. If the source of gravity's weakness is leakage, constant, passive bleeding of gravitational influence into these extra, large dimensions, then the force we experience in 3 dimensions is merely the residual effect. This phenomenon, known as large extra dimensions, offers a compelling explanation for the hierarchy problem, the immense disparity between the gravitational force and the quantum forces. Furthermore, this leakage could potentially account for the phenomenon of dark energy. If gravity is perpetually escaping into these larger spatial realms, the energy budget of our four-dimensional universe might be fluctuating in a way that manifests macroscopically as a repulsive anti-gravitational force driving the accelerated expansion of space-time. Dark energy might not be an intrinsic energy of the vacuum, but the observable shadow of gravity operating in a higher dimensional bulk. If these dimensions are indeed vast, the physics within them may operate under entirely different foundational rules. Moving up the dimensional hierarchy corresponds to accessing greater degrees of freedom, encompassing more possibilities within a single unified geometric structure. In a hypothetical fifth dimension, for instance, an observer possessing spatial awareness in that direction could potentially perceive all possible futures or divergent timelines originating from a single initial event simultaneously, collapsing the linearity of our perceived time dimension into a navigable landscape of potentiality. Extending this to the sixth dimension allows the observer to differentiate between universes that share the same initial conditions but diverge due to quantum fluctuations, the many worlds interpretation made manifest as a geometrically separated space. The seventh dimension permits the inclusion of universes born from entirely different physical laws, perhaps varying constants of nature. By the time one reaches the ninth and 10th spatial dimensions, the theoretical construct encompasses the totality of existence, every possible configuration of reality, every arrangement of matter and energy across every conceivable universe, existing concurrently as different spatial slices within this ultimate manifold. This concept brings us directly to the most audacious and unsettling hypothesis, that our entire four-dimensional reality is not fundamental, but rather a projection. Drawing inspiration from the mathematics developed to resolve the black hole information paradox, the holographic principle suggests that all the information describing a volume of space can be perfectly encoded on its boundary surface. If this principle scales up to the cosmos, our three spatial dimensions, along with time, merely the resultant shadows cast by the physics unfolding in the higher dimensional bulk. We are living within a universe-sized hologram. The perception of distance, the experience of motion, the very flow of time, all may be sophisticated computational artifacts arising from information residing on a distant, inaccessible surface bounding our perceived reality. The true physics, the complex geometries of the Calabi-Yau manifolds or the vast extent of large extra dimensions, remains forever beyond the direct sensory or experimental reach of the entities projected within the illusion. The yearning to experimentally verify these hidden realities drives the most expensive scientific enterprise on Earth, the Large Hadron Collider at CERN. While the public narrative often focuses on the search for the Higgs boson, the so-called God particle, which confirms the mechanism by which fundamental particles acquire mass, a secondary, perhaps more fundamental, objective is the active search for signatures of extra dimensions. If the extra dimensions are accessible at reachable energy scales, the high-energy collisions of protons within the LHC might generate exotic particles, specifically Kaluza-Klein excitations. These are effectively heavier, quantum versions of known particles, necessitated by the compactified geometry. A particle vibrating in a curled-up dimension would appear to us in 3 dimensions not as a single mass state, but as an infinite ladder of increasingly massive replicas, each step in the ladder corresponding to the particle oscillating with a higher frequency in the hidden dimension. Detecting any single member of such a ladder would confirm the dimensional extension. More dramatically, if the extra dimensions are large enough to significantly dilute gravity at the TeV energy scale, the LHC could potentially create microscopic black holes. These theoretical mini-black holes, formed by the extreme compression of energy, would immediately evaporate via Hawking radiation, vanishing in about 10 to the power of -23 seconds, far too quickly to pose any danger, even to the nearest atomic nucleus. The continued, though so far inconclusive, search for these Kaluza-Klein towers or transient microsingularities represents a direct, high-energy probe into the spatial fabric beyond our familiar coordinates. The narrative of modern physics, therefore, is one of profound uncertainty married to staggering possibility. We stand at a crossroads where the most successful theories describing the universe, general relativity and quantum mechanics, only achieve tentative reconciliation through the imposition of unobserved dimensions. The gravitational wave observation, the enduring enigma of entanglement, the nagging weakness of gravity, and the very structure of cosmic inflation all point toward a reality richer and more complex than the 4 dimensions we inhabit. These extra dimensions may be tiny, coiled like invisible springs at every point in space, dictating the fundamental constants through their precise Calabi-Yau topology, a topology perhaps capable of generating our specific universe out of an infinity of alternatives. Or they may be vast, siphoning off gravitational energy and explaining the accelerating expansion of the cosmos. If Kaluza's initial hunch, resurrected and amplified by Green and Schwartz, holds true, then the world around us is a profound simplification of a much grander design. Every object, every event, is subject to influences originating from spatial realms perpendicular to our own. When you lift your hand, the action is not merely a trajectory through 3-dimensional space, it is a complex, multidimensional maneuver through a space where the coordinates defining your location are constantly shifting in 6, or perhaps 10, directions. The air you breathe is not just a collection of nitrogen and oxygen molecules in 3 space, it is a dense matrix interwoven with the geometry of hidden loops that dictate the very strength of the bonds holding those molecules together. The very continuity of time, the relentless forward motion we perceive as an unalterable law, might be an emergent property, the projection of movement along a single axis in a higher dimensional space where temporal directions could be manifold, offering routes to past and future that remain orthogonal to our limited perception. The scientific caution surrounding these pronouncements is warranted. To declare with certainty that our world is a projection or that we are perpetually enveloped by 10 dimensions crosses the boundary from rigorous deduction to metaphysical speculation, a boundary that mainstream funding bodies and peer-reviewed journals traditionally regard with skepticism unless concrete, repeatable evidence emerges. Scientists do not dare. state this as established fact because the empirical proof remains elusive, locked behind energy barriers or geometric configurations currently inaccessible. Yet, the theoretical evidence is overwhelming enough to suggest that the quest for a true theory of everything inevitably leads us into higher space. The temptation is immense, the implications for philosophy, for our understanding of free will, causality, and the ultimate boundaries of physical reality, are staggering. We are, perhaps, sophisticated, self-aware patterns on the surface of a 10-dimensional entity, utilizing only a fraction of the dimensionality available to our true substrate. The universe may not be a simple story told in 4 acts, it might be a vast, complex, 10-dimensional epic, and we, bound by the limitations of our holographic perception, have only managed to read the prologue. The enduring mystery is whether we will ever develop the lens, be it a particle accelerator of unimaginable power, a detector sensitive enough to catch a single axion, or a mathematical realization that bypasses empirical constraints, to truly see the curvature and texture of the hidden dimensions that constitute the true reality upon which our perceived world is merely drawn. The journey continues, driven by the faint, unsettling possibility that everything we see is a beautiful, intricate lie concealing an infinitely vaster, stranger, and more geometrically resonant truth.